Good evening, dear all. Let us begin with the topic of electric dipole today again. But today we will find out the electric field due to electric dipole at a point on the equatorial plane. Now, what is the equatorial plane? We have already learned electric field due to electric dipole at an axis. So, what is the equatorial plane? That we will see, and we will find the electric field at that point. Then, in the next section, we will continue with the electric dipole moment definition and the difference between electric field due to a point on the axis and on the equatorial plane. So, keep maintaining your interest and watch this video till the end such that these topics are clear to you. I am Dhanu Saraiya with you today. Let's begin with the electric field due to electric dipole at a point on the equatorial plane. Fine. So here I have considered one dipole. We know how to construct a dipole. One is a positive charge, one is a negative charge, which is separated by a distance of 2a, where I have written here a. This is the center of the dipole and another a, so 2a. Now I have considered a point P on its equatorial plane. So where is the equatorial plane? It's here. Or it can even be down. I have taken a point P on the equatorial plane upwards. Fine. Okay. So now I want to find out the electric field at this point P, which is on the equatorial axis or equatorial plane. Fine. So now, as usual, what is our rule? Whenever we have to find out any electric field, what should we do? At the point P, we should first draw the direction of the electric field due to these two charges. So let's follow the same rule. So if this is a positive charge, then how should I draw the electric field? I should draw the electric field from the charge plus Q, go to the point straight outwards. Why outwards? Because it is a positive charge. Similarly, from the negative charge, from the point P towards the charge inwards. Why? Radially inwards. Why? Because this is a negative charge. So let us resolve these two vectors along the x-axis and the y-axis. I have resolved this vector. Now again I am resolving this vector, which is same on the x-axis and on the y-axis. Okay. So now we shall name them. Let us name this as E plus Q, vector E plus Q, which is indicating the electric field due to the positive charge Q. This as vector negative Q, indicating the field due to the negative charge minus Q. Let us also draw the direction strongly. And this vector I have resolved into two components, here and here. So let us name these two components also. For this vector, let me write it as E plus Q sin theta, E plus Q cos theta, horizontal component. Again, here for this vector E negative Q cos theta, horizontal component of this vector, and again the vertical component of this vector E negative Q sin theta. Sin theta I will write down so that it does not remove the R. Now here what is theta? Theta is the angle between the axis of the dipole and the line joining the point P and the charge Q. Similarly, the line joining the point P and the charge negative Q. That is theta. Also, we will denote what is the distance between the point P and the center of the dipole, that is R, which I have written here as R. So I am ready now with the directions of the electric field due to the charge plus Q and minus Q, and I have resolved these two vectors into its respective components. Those respective components are E plus Q sin theta, E plus Q cos theta, E minus Q cos theta, and E plus minus Q sin theta. These are the resolution I have done. Now again I use the principle of superposition for writing down the electric field on the point P due to these two charges. So what is the principle of superposition? E is equal to the summation of all the parts, right, or all the resolutions I have done, that is E plus Q is equal to E. Correct? These were my two directions of the electric field for plus Q and minus Q, which I resolved as scalars E plus Q cos theta plus E plus Q sin theta plus E negative Q cos theta plus E negative Q sin theta. Now, as can be seen, I have written scalars, that is, I have resolved these two vectors into its respective components. Okay, so as can be seen, these two components are opposite in direction and their magnitudes are the same. So, we can just cancel them out, that is, okay, and we can also at the end write the available direction. Now, what are the two components available to us? E plus Q cos theta and E negative Q cos theta, which is this side, which is seen here. So, our electric field will also be addition of these two components, which is against the direction of the electric dipole, which is always considered as negative Q to positive Q. So, here very carefully understand that I have written here a P cap, which will indicate the dipole, electric dipole, and also I am mentioning its direction here as negative, which is telling us that the electric field which we got is having a direction opposite, because of the negative, opposite to the direction of the electric dipole. Right? Okay, so this is the first part which we have to understand very clearly. I have broken the two vectors into its components, then I cancel these two vectors because they are equal in magnitude, opposite in direction, and I'm left out with only these two components which are in a direction opposite to the direction of the electric dipole itself. That's why I have written a negative symbol here and indicated the symbol of electric field and the electric dipole opposite to each other. That's why this negative symbol. Fine. So what am I left out with now? E is equal to negative I have outside. Then I have E plus Q. I can take cos theta common. And E negative Q taking cos theta common. And then I write P cap. I can as well write cos theta inside also 2 times. That also can be done. Whatever is convenient to you, that you do. But now we will find out the value, magnitude of E plus Q and E minus Q from the diagram. Now, for that I require the distance between the point P and the charge. So, how will I find out the distance? This is a right angle. So, I will just use the Pythagoras theorem, A square plus R square under root. Similarly, here also, this distance is A square plus R square under root. So, I am ready with the distance. And I also want cos theta. So, we will first write out these values here. That is E plus Q is equal to, what is our formula? K, Q upon distance square. What is the distance between the charge and the point? Root of A square plus R square whole square. Fine. E negative Q. Again KQ, though the charge is negative, I have already considered the direction. So again negative I shouldn't put here. Only the magnitude part. Okay. Root of E square plus R square the whole square. Fine. Cos theta. Look at the diagram and see me. What is the value of cos theta? What is the expression for cos theta? You can look at cos theta here. Cos theta is adjacent side upon hypotenuse. What is our adjacent side? A. Hypotenuse is again this root of A square plus R square. That we will write here. So is equal to A adjacent side upon root of A square plus R square. So I am ready with the three expressions, values. I'll just substitute here. Fine. Okay. Remember that I have to carry my negative sign. So I shall do that. And I'm also squaring in this step. I'm squaring this and writing here. So, and also I have K and Q common. So KQ also I will take common. So I'm left out inside with 1 upon E square plus R square plus 1 upon E square plus R square and cos theta, as I mentioned, is A under root A square plus R square, maintaining the vector P cap, indicating the direction of the electric dipole. Fine? Okay. So now physics is over. Always remember, when physics is over, math starts. Start your maths, and that time again, don't make a mistake. Don't make a mistake first in physics, and then next don't make a mistake in maths. You're done with it. Fine? Okay? So E is equal to, if I solve this, you can see I have both same quantity, so I can write it as 2. So negative k cube, both are same. So I can write it as 2 a square plus r square multiplied by a under root a square plus r square. This much maths can be done, but I'm just solving each step so that there is no confusion here. So E is equal to P cap, I will maintain, negative KQ 2A. Here the power is 1. Here the power is half. Adding both the powers, I'll have 3 upon 2. So I'll have A square plus R square whole raised to 3 upon 2 P cap. Yes. So ready with the formula for the electric field due to the electric dipole for a point on the equatorial plane. So let us box this result. Fine. So that we remember it as it is and note it down as a formula in our formula page. Now, once we get this result, we can make a small variation or a condition where we can say that R is very much greater than A. Never say A very much less than R. It is the same thing, but you should always speak as R greater than A. What does it mean? That the point which we have chosen, which is at a distance R from the center of the dipole, is very far compared to the size of the electric dipole itself, which is 2A or A. Fine. So let us substitute this condition here such that we neglect A in the denominator, not in the numerator. Fine. A is there definitely because we have taken the electric dipole itself with two charges at a distance 2A, so A is there. So neglect A in comparison to R in the denominator, not in the numerator. So keeping that condition in your mind, E is equal to negative KQ 2A P cap, fine, divided by, I am neglecting R square from here, so I have only R square. I am neglecting A square from denominator, so I have only R square. So fine, cancelling these two, I have E is equal to negative K Q 2A P cap upon R cube. So this is the value which we get for the electric field due to electric dipole at a point on the equatorial plane for the condition R greater than A, which means that the point which we have chosen is far big compared to the value of A itself. Right? Okay. So with this we move to the next section where we will now actually define electric dipole moment. It is also called as dipole moment. It's one and the same. Fine. Why? Reason, because in the electric field, due to the axis, point on the axis, we had got 4AQP. Here we have 2AQP cap. So there may be some quantity which is going to define this portion of the expression which we have got. So let us define electric dipole moment in the next page. So let us define electric dipole moment or simply dipole moment as said earlier. So it is a vector quantity whose magnitude is q times the separation 2A between those two charges plus q and minus q, and its direction is always from negative q to positive q, which is already learnt by us. So let us write it as a vector. P arrow is equal to q into 2a p cap, where p cap denotes the direction minus q to plus q. Okay, and its unit is as seen from here, charge meter. 2a is a length, so in meters. Q is charge, so coulomb. It is not centimeter. Remember that confusion comes. It looks like centimeter. So you remember, C has to be written big, capital, and M has to be written small. C is the unit of charge, that is coulomb, and M is the unit of the length, that is meters. Fine. Now from here, this definition or this formula, we will come to the electric field, which we derived already at a point on the axis, at a point on the equatorial plane, which we have already derived as E is equal to 2 Q to A P cap upon 4 pi epsilon naught, which is K R Q. And here also we can see E, electric field, is equal to negative Q to A P cap upon 4 pi epsilon naught R Q. Here we can understand that this portion is the formula we just now wrote as P arrow. Here also this portion is the formula as we just now wrote P arrow. That is the electric dipole moment or simply dipole moment. So now we rewrite E is equal to 2 K P, where K I have written as 1 upon 4 pi epsilon naught R cube. And here we write the direction of P as P arrow, and without forgetting the negative symbol, we just write KP arrow, that is P vector, divided by R cube. Okay, so sometimes the comparison can be asked. What is the comparison? The first comparison which you can see here is that the electric field is in same direction as P arrow, that is a P vector, electric dipole moment. Direction is same. Here, because of the negative symbol, E arrow is opposite direction. I write direction as small 2 P arrow, that is the dipole moment. That is the first observation. Next observation, in magnitude, this is twice. Let me write this as E axis, and let me write this as E equator, EQ. So what can we found out? That E axis magnitude is twice E equator. That way also question can be asked. And here I can write E equator's magnitude is negative. That is the direction. If I don't write also, it is okay. It is half of E axis. Am I right? Both the ways the question can be asked. I need not write the negative symbol there because I am talking about the magnitude. Fine. Then what else can we write from here? We also can write that in both the cases, E is inversely proportional to R cube. E is inversely proportional to R cube. Okay. So whether this or this point, I'll put it as stars and you can remember it as formulas. Okay. They are all P by Qs, but the condition which has to be written in the question is R must be very much greater than A. Only then you follow this. Fine. Okay. So for R very much greater than A, much greater than A, that means the point which you selected is much greater than the length of the dipole itself or dipole axis itself. Then these conditions shall follow. Okay. So now I just move, you take a picture of the comparison I have made and the electric dipole moment definition.